I want to talk just a little bit about heat transfer. We've talked about it sort of by implication when we've talked about putting two objects together. And when we have two objects in contact, then we're talking about heat transfer, like this is temperature 1 and this is temperature 2 and T1 is bigger than T2. Then we're talking about conduction. Okay, just so you have a name for this. And conduction is the transfer of heat energy when things are in contact and the particles that are like on the edge of this that are really warm and excited have a higher energy, then transfer that energy to the neighbors that they're in contact with. So this is a way that we do energy transfer, obviously, on stovetops. If you have a stove where you put something metal in contact with your heating element, and so that's heating by conduction. You can then transfer heat energy also by convection. Can't spell. And this is really by fluid flow. It's air or water currents, typically, at least naturally. So this is really having to do with the density change. So as you have air that's warmer, it expands, which makes it less dense and it rises. And so you set up convection currents in a room. You can set up convection currents, obviously, in the oceans. We have convection currents there. So this is typically, you can also have what's called forced convection with heating elements and blowers, right? That's blowing the air and forcing the circulation. That's what our AC systems are. And then we have radiation as heat transfer. And so radiation is by E&M waves, electromagnetic waves, which we will get to much later in the semester, the idea of electromagnetic waves. But this is, of course, the only form of heat transfer that can happen in a vacuum. So this is how the sun's energy gets to us. It's in the form of radiant energy. And the type of energy, the amount of energy and sort of the type of energy we have really depends on the color of the light or the wavelength of the E&M waves that are bringing us this energy. And you're familiar with this already. And so we often describe this lambda is our wavelength. And we talk about the intensity, how high it is, how much energy we're getting, and it depends on our wavelength. So, or the color of the object, actually. So we can have something like this, where this might be something that is almost like the color of the sun, sort of a yellow or even white hot, like the center of a flame that gets a white hot color. And so this is going to be mostly in the visible, so that wavelength will be peaked in the visible, where this is a shorter wavelength is ultraviolet and a longer wavelength is infrared, IR. Whereas like something that glows red, like embers from a fire, that's going to be still in the visible, obviously, because you see it, but it tends to be sort of over here. So this might be something that's red hot, or even something that is shifted over even more that emanates in the infrared. We do that. We don't glow a certain color, but we give off infrared radiation. Everything in the room gives off infrared radiation. That's how it's certain warm or not to the touch. Well, okay, once we touch it, then we're talking about conduction. But as we get close to it, we can feel infrared off of stoves and things like that because it's a different temperature than our skin. But everything gives off infrared, and just how much and what wavelength depends on the temperature of the object. And then something that's blue, like the blue flame, you're going to be peaked here at an even higher temperature. The point of all of this is that sunlight comes to the earth, and I just want to make sure we see this. You know about this already, and we're not going to spend a lot of time calculating it. But when we look at radiation that comes from the sun, we get ultraviolet, as you know, because we need sunscreen to block the ultraviolet. We get visible because we can see the sun, and we get infrared, but it's mostly peaked around the visible. But what happens is the Earth then absorbs it. The Earth's surface absorbs this energy. It doesn't heat up a lot. I mean, it heats up just a little, but the Earth is at a pretty stable temperature. Global warming certainly is happening, but that's not a big fluctuation. It's not like hundreds of degrees. So what happens is the Earth radiates this energy back out. So this energy comes in, but because the Earth is not as warm, it radiates energy back out as infrared. So it's like peaked. It's actually probably over here. There's the Earth, for example. And the clouds, it's not really clouds, it's the atmosphere, sorry. Clouds do reflect it back in, but it's really the atmosphere, the water, and, as you know, the carbon dioxide that trap this in, that reflect it often back down. It also takes some of course, this sunlight that comes in, hits the atmosphere, and that gets reflected off as IR as well. And so it gives us what we call greenhouse warming. And you see this same thing happens for your car. Sunlight comes in, it comes in certainly as visible through the car windows, and then the seats, for example, are radiating back out in the infrared, and that gets caught by the glass. The infrared can't get through the glass, even though the glass lets visible through, right? I mean, there are other parts of your car that don't let the visible through, right? That's in your trunk. Or if you put the sunshades in, right? That doesn't, that visible, that blocks the visible some. I mean, it still gets through the glass. It makes a little area that's pretty warm right up against the glass. The point is that this greenhouse effect is actually, to start with, good for the planet, because if we didn't have an atmosphere, if we couldn't trap water and carbon dioxide gravitationally, then the predicted temperature of the Earth would be not habitable for us. So in general, we need some amount, obviously, of water and carbon dioxide in our atmosphere for lots of other reasons, and that keeps us at a nice temperature. But of course, as you know, as we change this, as we tweak this, particularly this amount, just a little bit, we can really change this balance of how much we're radiating back in and have a pretty big effect of how much IR we end up radiating back to the Earth and increasing the temperature. So I just wanted to note that this does show up, and it's really about these molecules that won't let, sort of like glass, lets visible through, but doesn't let IR through it, and so that can heat things up. Okay, and that's our greenhouse effect. But as we're looking at, I'm not going to ask you to do calculations on conduction, certainly not convection. Convection currents are really, you have to know a lot of fluid dynamics to be able to do anything with them. And then this radiation balance we may get to when we get to electromagnetic waves. But it's something to keep in mind. It really does depend on our wavelength as we're going along.